Hi, everyone. Welcome to J Champions Conference 2022. This is organized, run, and presented by Java Champions. I'm Melissa McKay, and I'll be moderating this session, Novel Uses of Core Java. Our presenter today is Java champion Peter Lawrey, who you may recognize as having the most answers for Java and JVM on stackoverflow.com. For those of you online, I'll be monitoring this chat for any questions. If you would like Peter to answer them, feel free to post those at any time during the session, and we'll have some live Q&A afterward with Peter right after the session. And with that, I'm going to hand the virtual stage over to Peter.
Okay, so 8 years ago, I started a company which was largely open source to start with. A lot more closed source today, but it's certainly still a significant amount of open source. And I realized that actually some of the things that I did in the open source were novel. They're not the sorts of things that Java developers would normally come across or would do. And I thought it was worth at least documenting and might be interesting even as a talk. So one of the first ones that I'd like to talk about is that I actually have a class called Stacktrace. Now, what is novel about this is that it's not an exception and is not an error. It extends Stacktrace. Now, so some things about to note straight away is that I do actually use Vedanta as my font for editing. So I don't use proportional font, which I think I'm in the minority for, but there you go. Another thing is that classes that extend throwable are checked. So you probably never wondered whether that was a problem or not, but classes, it is a checked exception or a checked throwable in this case. Another thing to note is that throwables take a stack trace for when they're created, not when they're thrown. So there's no need to throw a throwable just to get a stack trace from it. So it's very normal to just throw a new whatever exception, and it's all in one line, so you never need to think about, well, where does the stack trace actually come from? It doesn't come from throwing it, it comes from creating the stack trace, the throwable object. Another implementation detail about throwable is that the stack trace itself is stored inside the object, but not in a form that you can see. This is done for efficiency purposes. The stack trace itself is only constructed when you ask for it. So that reduces the overhead of creating these throwables. But to get down to this specific class, what does this do? It essentially captures a stack trace. So you might think, well, why not just have a class that wraps a stack trace? But it actually has a lot of side uses, indirect uses, by making it throwable. And one way to think of it is a deferred exception. And I do actually use it as an exception in many cases, but never at the time it's created, because it's largely for tracing and diagnostic purposes. So here's an example. So say you've got an object that is closable, and you want to make sure that it's not used after it's closed. Now, one of the problems with this is that often it's difficult to determine, well, if I use an object and it blows up because it's been closed, why was it closed? You know, where was it closed? This is particularly relevant for long-lived objects. So here's an example where I take a stack trace for where it was closed, and then later I throw, in this case, an illegal state exception with the type being closed. Where it was recorded. And the way it comes out in the stack trace is you can see that not only am I recording the location where it was called, so you can see the code that triggered the close, but I can also show that the thread, so I've got the thread name captured where it was closed. So you can see in this case that it was thrown in closed in another thread on a particular line of code. And that can really help diagnose, well, I'm trying to use this resource after it's closed. Was it closed correctly or prematurely, or was it that I'm using it long after it should have been used? And this can really help diagnose it. And this all comes down to the fact that this Stacktrace object is actually a throwable. Otherwise, I couldn't make it the cause. So you can see in this case, illegal state exception. The cause of this exception is the Stacktrace that I collected earlier. It wouldn't work if that wasn't a throwable. And there are many other cases. So this is useful for reporting and monitoring. So another one is, say you have a resource that needs to be deterministically closed. So a good example, just in the Java library, is, say, random access file. Now that, even though it will be cleaned up, even though the memory will be freed when it GCs, the file handle, what doesn't get cleaned up, it doesn't get closed. So if you just create lots of random access files, eventually you'll run out of file handles, because when it closes, even when it collects it via the GC, it doesn't close the file handle it's associated with. So you have to determine, you can get a resource leak. And we have components that are kind of similar to that, where unless it's actually closed properly, you can get a resource leak, not just freeing up the on-heap object, but there's an off-heap object associated with it. And so it can be useful to trace, well, if I have an object that wasn't closed correctly, deterministically, how do I trace this? So in this case, what happens is that I'm logging where was the object created. So I've got a resource that was discarded, it wasn't closed, but I want to also include some information that would help me trace where was it created, because that can help me work out, well, why wasn't it closed? So in this case, it's a fairly simple one. I create an object, I GC, and I wait a little bit to make sure that it's all the background threads do their job. And we get a message out which shows where this object was actually created. So then I can work out, well, through the life cycle, how is it that this was discarded without being closed correctly? So another, and again, you wouldn't be able to log it like this if created here wasn't a throwable. So it needs to be a throwable for this API to work the way it does. Here's another example. Say you've got an event loop, and your event loop is periodically running slow. So occasionally you've got some jitter, your event loop is sticky. And these are very hard to diagnose in development. And when they happen in production, you want to capture them. And so there's a very easy way of doing that. You have a loop, which every time it goes around, it updates a loop counter to say when that loop was started. And if that loop has been running for too long, so it's been stuck in that loop, something has paused, it can be very helpful to be able to take a snap trace of it so that you can see, oh, this is where my event loop got stuck for a short period of time. Now, in this case, it's all in milliseconds in this example, but I've done this successfully trying to diagnose problems down to 20 microseconds, being able to capture why is it that the thread is occasionally taking 20 microseconds longer than it should. So you can get some very fine-grained stack traces that, and you can have this running in production because the overhead is extremely low. It's quite high when you take the stack trace, but you're hoping that that's valuable. But when you're not taking stack trace, all it's doing is every time it goes around the loop, it updates a timer. It keeps resetting a timer. Another use for taking a stack trace is being able to programmatically detect when a resource you've designed to be single-threaded is accidentally used across multiple threads. So in this case, what the resource does is it takes a stack trace of where it was first used and also records which thread used it. And then what it can do is it can say, well, if it's used by a second thread, that's not the first one, you can actually throw an exception. So what the code looks like is, in this case, I'm creating a thread. The thread uses that and then starts and finishes. It's no longer running, so that's another thing you can check for is the use thread actually still running before you complain? But in any case, you can see in the Stacktrace down the bottom that you can see where it was used for the second time, but you can also see lower down on the Stacktrace the cause being a Stacktrace that it was first used by a thread called resource user. And you can see where it was first used. So this can be enormously helpful in trying to diagnose those problems. Now, you might be wondering, isn't this pretty heavyweight? And the answer is yes, it's very heavyweight. However, most of these libraries are quite comfortable with taking null. So if you want this feature turned off, and you can make it through, say, a system property, you can just replace it with null. You don't need to take the Stacktrace. So in this case, the code, if you throw an illegal state exception and used here was actually null, then it wouldn't do anything. There's nothing to worry about. It would just not have a cause. It would detect it, but it would have no cause. In this case, if we go back to this one, logging, for example, if created here hadn't been set to anything, it was just null, then you would still get a log message. You just wouldn't get any Stacktrace. So it's very easy, and it doesn't complicate your code too much to have just a simple flag turn off this feature when the overhead is too high. So this is the most convoluted example, and it shows up some features of throwable that you may not have been aware of. And that is that what this does is, say you've got a test and you want to make sure that there's no threads still running in the background that shouldn't still be running. So you take a snapshot of all the threads that are running before the test starts, you run the test, and then afterwards you check all the threads that are still running. And you want to detect when there are more threads running. They won't all shut down. But you don't want to just detect them. You want to find out, well, what were they doing? And who created them, right? So where did they come from? Why are there threads here? And what are they still doing, which can give you a hint as to why they didn't shut down. So that's what this code can do. So it's about halfway down. It's got it tries to capture where the thread was created in the first place, if that is available. It's not available by default by a normal thread, but you can have a thread that adds that. And then it takes a stack trace of what that thread is doing right now, which it was captured when it got all the stack traces. And so it actually now has a throwable called Stacktrace, which has two stack traces. One is what's it doing now, where was it created? But overall, at the end of this loop, it's going to throw one exception, which is an assertion error. And that assertion error has in it all the stack traces of every thread. So the way this is added in is by using add suppressed. So you've got all these suppressed stack traces, one for every thread that's still running. And you get a really long message if there's a lot of threads, but you can see in a lot of detail what are all the threads that are still running that shouldn't be, what are they doing, and where were they created, so you can try and work out what was wrong with their life cycle. And none of that would work if Stacktrace wasn't. A lot of that would be very difficult to implement if that Stacktrace wasn't a throwable. So you're using the machinery of a throwable to hold that. So just moving on to another topic. So this is a little feature that we make use of to do with profiling. So in theory, although not in practice, in theory there's a save point between every bytecode instruction. However, having a save point, which is a point at which a thread could be stopped, is pretty expensive. It adds up. It's not actually expensive in itself, but added into all over the place, it really add up and be very expensive. So what the JVM does is it essentially goes through and tries to remove as many save points as it can without compromising its ability to be profiled too much. But it doesn't always get that job exactly right. It doesn't always get it quite the way you might like. And so we've got an operation which essentially adds back in a save point, which is very lightweight, into key places where we know there could be a profiling issue we want to pick up So its overhead is very small because we only add it in places that are not inside loops. For example, Java 8 had a very simple instruction you could call that triggered a save point. Java 9 plus optimized that away so it doesn't exist, but there's another way of tricking it into producing a save point, and so we use that. And this is going to be very useful when you've got, because when you're profiling, or even previously when you're taking stack traces, the thread has to reach a save point to get proper profiling. So adding these save points in can give you more clarity, particularly if you suspect the line of code that's being blamed or the method call that's being blamed isn't actually the one that's doing the most work. I remember one time integer.hashcode was blamed for it was the third biggest CPU user. But if you have a look at the implementation for integer.hashcode, you'll see that it doesn't actually do very much. So that's an example where it was suspicious that what was being blamed was really the cause of most of the CPU usage. Another thing that we use, which is surprisingly handy, again, it's more around monitoring and tracing of the system, and that is generating distributed unique timestamps. So internally, we use nanotime resolution timestamps. We've done this for a few years now, and we've got a number of different implementations for generating it. But one of the things about these timestamps, even though they're very detailed, they're almost, you can use them for tracing, like tracing an event through the system by looking for a timestamp. But there's always a risk that actually there's duplicates, like that timestamp could appear more than once across your system, even within a system. So we have a solution which actually makes sure that timestamp is genuinely unique. And one of the ways we do that is through using shared memory. So halfway down through the code, it's got a compare and swap, this is a happy path. A happy path is that there is no duplicate timestamp. And what it does is it adds in a preset host ID so that your timestamp will have a host ID in it. And that way you can generate a unique ID. This is the happy path. The less happy path is that the previous timestamp generated on that machine already is either newer or the same, probably the same. And so it has a loop where it goes and gets what is the most recent one, tries to get the next one, and sits in a loop until it successfully can acquire a new timestamp which is higher than the most recent one issued. The way this ends up looking, because it's a timestamp, is it looks like a regular time, which is quite nice because it's relatively readable. It saves you also having to take another timestamp as well as having a tracing unique ID, because it's unique itself, and essentially puts the host ID in the last 2 digits of the timestamp. So you lose some resolution. You can only get 100 nanoseconds timestamp resolution, but that's usually enough. It means a single machine can't generate more than 10 million IDs a second for a sustained period of time. Otherwise, you start running ahead of the wall clock. But as long as you don't do that, you can end up producing unique IDs that won't reoccur, even if the machine is lost. By the time you restart, time should have progressed enough that you won't end up with any duplicates. It's 64-bit, so this information will be stored in a 64-bit value. And it's an alternative would be to say use a random UUID. Now, random UUID is actually more expensive, and it does create a little bit of garbage, not much. But it has the disadvantage that not only is it bigger, it's 128-bit, but you may still end up wanting a timestamp anyway. So you you don't really save very much in that regard because you probably want to have some timestamp tracing anyway. So you're only adding to what the work that you had to do. So this unique timestamp ID is very efficient. It's about, on newest hardware, it's around 40 nanoseconds. So it's pretty light. And it's one of the fastest ways to generate any kind of ID. So moving on to probably the most surprising thing that we do is we do make use of what in C++ would be called a trivially copyable object. So in C++, there's a concept of, it actually has a compiler check for this, that you can test whether a data structure is what's called trivially copyable, in that it can be just a memory copy can be done of the whole object, and then all the data is preserved. So we have a slightly modified version of that to fit within Java. But we can take a data structure like this, which, so this is what it looks like when we dump it out as YAML. You can see the type. One of the nice things about YAML is that it allows you to have, it has direct support for types. It also is a little bit cleaner in terms of syntax, in terms of having a lot less quotes that it needs to have. One of the downsides of actually implementing a renderer for YAML is that it's designed to be human readable. So human readable is good for humans. It's a lot harder it's a lot harder to code human readable, right? Generate it, but also make it the most human readable way you might want to write this yourself, if there's like 2 or 3 ways of rendering the same thing. So it actually is, it's quite tedious to create a good renderer for YAML for that reason. And I can't claim to have done a perfect job, but it's not too bad. So what does that look like? So you can see here that most of the fields are primitives. And all the fields that are primitives here can be trivially copied. This comes with obviously a lot of caveats, like you're assuming that the arrangement of these fields is going to be the same on the machine that's deserializing it as the one serializing it, which is a big assumption. However, if that assumption holds, you've got an extremely efficient way of copying the data. So one of the things that you'll notice that we have to support that is the ability to turn text into primitives and vice versa when you want to dump it out as YAML, for example. So obviously the date time, it makes a lot of sense to store it as a long, but when it's in a human readable form, you want it as text because that's just much easier to work with and to read. But we can also do that for short strings. So if a string fits into a 64-bit value, then we can convert it with whatever base you choose. One of the simplest is obviously base 128, which stores up to 9 ASCII characters. For longer strings, they still have to be strings. And so, so you can't trivially copy all of this. We do have a mechanism for making all trivially copyable, but if you use strings, then some of it isn't. And so you have to write a little bootstrap code here. So you can copy almost all of it as a trivially copyable object, but the 2 strings involved need to be written individually. And the nice thing about this is that we can get relatively large data structures copied in tens of nanoseconds, maybe a few hundred nanoseconds for some of the larger objects. So the cost is extremely low. Excuse me. Something else that we do, which I think is a bit more unusual these days, is zero garbage coding. So we still advocate very low garbage, creating very low amounts of objects. And that's really about reducing jitter, and it's about reducing work. So there is a bit of an overhead creating garbage, and that garbage creates pressure on your cache. So it's pushing certainly your L1 and L2 caches out by scrolling through memory, creating all of these objects, pushing out data that you may want again very soon. But also it does cause some pauses, and so it can be useful to. That's interesting. It can be useful to reduce jitter as well. Now, this is so I did a benchmark recently of a messaging system, open source messaging system, and this is the amount of GC activity for the client. In this case, just in 1 minute to do 60 million messages. So it's not unreasonable. This is fairly normal for a Java application. I'm not saying it's bad. However, it doesn't have to be that way. You don't have to just accept that when your application is busy, it's going to create garbage like mad. So in this case, each of these columns is 2 seconds. So even though it's sort of hovering around 13 gigabytes, that's every 2 seconds. So it's producing about 6.5 gigabytes a second of garbage, and that's creating a lot of memory pressure on your caches. Even your L3 cache is going to be pushed out in a matter of milliseconds. So if you go back to retrieve some data you used a moment ago, it's already gone because the amount of garbage has just pushed it all out. So this is running the same workload using Chronicle, right? So this is again 60 million messages. Each message is around half a kilobyte. And what's interesting about this is that all of the top hitters for garbage are actually Flight Recorder. So it's only producing about 300 kilobytes a second, which is very low compared to 6 gigabytes. But even then, more than 90% of all of the garbage is actually just it's using Java serialization for taking metrics from the JVM. It's not actually the application running. So that really sort of highlights how clean you can make it if you really need to. Now, for some reason, the memory usage graph doesn't show anything. I'm not sure why. I would think it should show something. But you can see in the allocations that it's every 2 seconds. It's about 600 or so kilobytes. So how much difference does this make? Well, if using a lot of the techniques that I mentioned before, we've got things like shared memory, which I showed in the timestamp example. We've got trivially copyable, which is just very low level serialization. We've got another thing we use quite heavily is for reducing jitter is binding threads to isolated CPUs so that they're not having to, that CPU isn't having to contend with doing anything else. So they're dedicated and assigned, and it can significantly reduce the latency end to end. So in this case, it's a benchmark of sending messages to a microservice and then timing how long it takes to get the reply for the message that I showed earlier. And the difference is more than 2 orders of magnitude. So it's about 700 times roughly for most of these scales on the metric. So, and it's doing the same work. So from the microservice point of view, it's exactly the same. It gets a DTO in and it produces a DTO out. All the rest of it is essentially overhead from its perspective. So you want it to be as fast as possible. You don't necessarily want to wait around for this. So, and that's why we do a lot of these things. It's about reducing latency and reducing overheads so you can get much higher efficiency. So we also have so this is a little micro optimization, is that we have a spin loop. This was actually originally proposed by Gil Tene. Is just a hint to the compiler that this is a busy loop. So we do actually use a lot of busy loops, more than normal code would. Not that many, but it is an important feature. So we use busy loops because we don't want to necessarily give up the CPU, because whenever you give up the CPU, you're adding a lot of jitter to your application. So, but you don't also want to just burn CPU unnecessarily. So we can put in this nanopause, and that can help reduce CPU usage a little. Another feature that we use quite extensively throughout our code is caching decisions to do with a class. So say you've got a class, we want to generate, for example, some data associated with a class, like how do I serialize it, how do I deserialize it, how do I take an interface and make all the methods, every time you call them, it turns into an entry in a queue, for example. A lot of those decisions we want to cache. We don't want to be doing it every time, so that once the code's warmed up, it's running as efficiently as possible. And Java 7 actually has a feature to do that called class value. Unfortunately, the one thing it lacks being Java 7 is there's a Lambda support. So we have a variant which allows you to specify a Lambda for creating the initial object. So, and this is an example where we want to have an accelerated read resolve. So what happens here is that this is only called once for each class. And if the method's not available, it will become null. And one of the nice features of this is that if a class is unloaded, it will be removed from the cache as well. So we don't need to worry about life cycle of classes. So it's a very elegant way of caching some decision to do with a class, which would be very expensive to do each time. One of the things that we make use of, which again is perhaps a little bit surprising, is we make use of vicarious exceptions in certain cases. When I first started using this, like a lot of things, when you have a hammer, everything looks like a nail. So I ended up overusing it. You can overuse this feature, but I did later do a review now 5 years ago. 5 years ago, and removed a lot of them. But there were certain situations where having a vicarious exception was actually very useful. And one of them is being able to pass checked exceptions up through interfaces which are not checked, so that they can still be caught as the original exception without having to wrap it and then unwrap it, which is an alternative, but I think it's actually more painful than just throwing up the actual exception. So use it carefully, but in the right situations, it's very handy. It's mostly useful when you're throwing an exception through your own libraries. So you're the thrower and the catcher. If you do this and you're expecting someone else to catch it, that could be quite confusing unless it's well documented that this exception can be thrown. One of the things we use extensively is doubles for our calculations. Now, a lot of people would prefer to use big decimal, and I understand that. Big decimal is easier to reason about, but one of the problems I've seen again and again with big decimal is that if you've got a precision error in big decimal, it's harder to spot. So with double, if you've got a precision error, and it's very easy to get them, it's quite easy to spot. You get this 00001 or 9999998. It's very easy to say, that's not right. Got some sort of rounding representation issue. And you can also work out what it probably should have been just by rounding it either in your head or in code. All right, so it's easy to spot, and it's relatively easy to correct for. However, with big decimal, if you have a precision error, the problem is you always get a number that looks reasonable. So simple example is, say you divide 1 by 7, and then you multiply it by 7 again. If you do that incorrectly, you can end up with a number like 0.98. If you say do it to 2 decimal places. And the problem there is that if you see 0.98, you won't immediately say, oh, that's a representation issue, or there's a rounding issue. It looks like a reasonable number, but it's wrong. It can be harder to spot that you've made a mistake with big decimal. So apart from whether it's any more error prone, and obviously different people have different opinions as to which is more error prone, big decimal is also still substantially slower. It used to be a lot slower, but now there's some significant improvements, and it can be fast enough. So this is doing a matrix by vector multiplication and timing how long it takes on different versions of Java. There's a little bit of variation between different versions of Java, but there's real consistency between that double is substantially faster than big decimal, and this is apart from the fact that double, of course, is primitive, doesn't create any garbage, and supports things like trivially copyable. Whereas big decimal is an object, and it's kind of expensive to serialize and deserialize. So one of the things that we do is, because we want to have low jitter, and we've got resources that we want to be able to clean up deterministically and not just wait for the GC, partly because we hope the GC never runs. As we saw in the previous example, no real allocation, so we're not looking to have the GC run at all. So waiting for the GC to run to clean up our resources indirectly is probably not ideal. So, because you just don't know how long that might be. It might be hours before a GC is run. And so that then the resource could be just hanging around. So you could have a file, for example, that you can't delete because it's just waiting for a GC to clean it up and close it. So we have all of our threads that we generate are subclassed as a cleaning thread. And what that does is that when the thread dies, it actually goes through any thread locals there are, and it has an API which allows any thread local associated with the thread to be cleaned up. This is kind of very hacky and horrible, but nevertheless, it's, as far as I can work out, the cleanest way to ensure that resources associated with the thread are cleaned up when the thread actually dies, not some time later, which again, is in our case, we're actually trying to put off as long as possible because we want it to GC as little as possible. So one of the things we do, particularly with deserialization, is we try and object pull the strings if that's reasonable, and that can reduce a significant amount of garbage. Depending on the situation. If you've got a relatively small number of strings and they're not very large, then you can have a pool of them. The problem with a lot of object pools is they can easily be so expensive to maintain that they're actually a lot more expensive than just creating a new object. So how do we create a really lightweight object pool for strings without that aren't going to cause more overhead than they're worth? And so this is a technique that we actually use as just an array of strings. There's no keys because the strings themselves are the keys. There's not one that you can see in this code, but 2 attempts to find a string in that array. And if it finds a matching string for the character sequence, which could be a string builder, for example, then it returns that string instead. If it can't find it in either of the 2 spots that it will look, then it goes and has to create a new string. Right? So it only does a fairly weak attempt. However, if the array is big enough, then you've got a pretty good chance of having a high hit rate for caching these objects, and the overhead is very low. In terms of benchmarks, the cost of doing this on a per call basis is typically about the same as creating a new object. So you might be wondering, well, what's the point if it costs about the same anyway? The difference is that using this approach, depending on how effective the cache is, it can reduce your garbage. And in extreme cases, like you saw before, reduces it to nothing because it's actually got the same string every time. So that is the reason. And it's all internal to the library, so you don't have to worry about it. It's just something that it does on your behalf. So it works quite nicely. Now, the reason I mention it, though, is what makes it interesting is that this class functions correctly without any explicit thread safety guarantees. So it doesn't use locked, synchronized memory barrier, any kind of explicit memory barriers. So there's no volatile, there's no fences explicitly in the code. And the reason that works is that a string has final fields, and those final fields are guaranteed to be visible when the string is created, without any further any further features used to ensure that it's visible and correct. So that means that a string can be used in another thread, passed to another thread, and you won't see a slightly uninitialized string or completely clear string accidentally, no matter how you pass it through to another thread. Another thing is that the array works correctly as a cache, even if all the threads involved don't see the same view of that array. So each thread could have its own idea of what objects are in that array, but that doesn't matter because it's just using whatever its local copy is. It could have different strings in there, but as long as it has a good hit rate for the strings that it's reading, that all works fine. So it's kind of a bit odd in the sense that, like I said, it's a data structure that's somewhat complex, doesn't require any explicit thread safety guarantees, and that's part of the reason why it also is very fast, because it doesn't require volatile or any kind of locking to function correctly. And it's because it's only it's a best effort class as well. So because it's best effort, when there is some sort of weird inconsistency, like it suddenly gets some of the array from another thread that use different strings, it will still function correctly. It just probably won't get the kind of cache hit rate that you might have expected. One of the things that's always annoyed me about the documentation is unchecked exceptions. So certainly in our documentation and other documentation I've read, it will mention that you can get unchecked exceptions which never actually get thrown, or it will fail to mention unchecked exceptions which can easily get thrown. So how do you reconcile that? How do you check that without going through it very manually? And one of the ways to do that is that we've only got a small number of unchecked exceptions, which are the parent of all the exceptions that we have. So we've only got about 5 unchecked exceptions we really care about, and all the other exceptions are subclasses of that. And what we can do is we patch in a checked version of it. And then what happens is that all the code goes through and it says, you've thrown it here, and it doesn't compile, right? You didn't declare it as throws, which is perhaps unfortunate because people don't necessarily like to see unchecked exceptions in the throws clause. However, you trace it all the way through to your documentation, and you can then see, this is throwing an unchecked exception I haven't documented. The first time I did this, it was a bit of an eye-opener because there was actually quite a lot of code where it caught an unchecked exception and then effectively either ignored it and logged it and continued, or handled it very badly, or threw an assertion error, something like, this should never happen. So it caught an unchecked exception, says something like, this should never happen. And in fact, doing this showed that it genuinely never happens, right? There was genuinely nothing that ever threw that unchecked exception. So I was able to just delete quite a bit of code that really shouldn't have been there, because I could actually see provably that unchecked exception is never thrown anyway. So this is something that's handy to put in occasionally. I do it about once a year, go through the code and put that in, see how our documentation is going, see if there's any kind of strange handling of unchecked exemptions, it can be good for a review process. Now, the last one is a little bit lighthearted. So we have our own interface for exception handling. The reason we do that is that in all of our tests, we check that any message logged or any exception reported is an expected one. So by having our own framework set on top of SLF4J, during the test, you can record all of the messages reported, any exceptions that were thrown, and then check that they were expected ones. So we have tests fail if it starts reporting an exception that, even though the test notionally passed, if it reported an exception or produced a warning that wasn't expected, a new warning, then the test itself fails. It has to expect that warning will be produced. So we have an interface called an exception handler, which can be mocked out to be recorded for testing purposes. But I've got this one, which is just sort of an assist, where if an exception is thrown, it attempts to open up it attempts to open up in your browser a Google search for the exception. So one of the simplest ways to try and diagnose an exception is to take the message and Google search it and see who else has ever had that. Well, this will do it for you. It actually goes and opens it up in the browser for you. It would be tedious if this happened a lot, but just a sort of amusing aside. Okay, so we're coming near to time. I think we've got at least probably 15 minutes. Does anyone have any questions?
Hi there, Peter. We definitely have a few questions that came in while you were talking. I'll do my best to give you the context around them. The first one that came in was from Mark Falco. This is when you were speaking about stack traces in the beginning. And he asks, constructing a throwable and computing the stack is still quite expensive though, isn't it? And I think you addressed this a bit during your talk, but you may have more to say about this.
Yes, so it is very expensive. However, if you take this example here, you can see that I'm logging this created here. When we have this flag, a property called resource tracing as a property, and by default it's off. And when it's off, the created here is just set to null. So it just says created here equals if resource tracing is true, then take a Stacktrace. Otherwise, just set it to null. So the default behavior is that all of these stack traces are actually null. And so they don't do anything. And a lot of the handling code handles it just fine, because when you log it with a throwable of null, it just doesn't have it still gets the message, it just doesn't have a stack trace. Same thing happens when you provide it as a cause for an exception. So for example, here, say closed here was null, you would still get, it's just because of this dummy example, the way it's written, it should really be a flag. It shouldn't be checking the stack trace. But if it was a flag, you say if closed, you say throw a legal state exception closed, and you would have closed here. But closed here would be null, which is fine. So you end up with just an illegal state exception with a message, but no stack trace as to what caused where it was actually closed. So it's very easy to turn off, and in fact the default is that it is off. We turn it on for all of our unit tests. So when the unit tests are running, they're on, but the default behavior for production code is that it's off. So you're right, it is still expensive. It's not quite as expensive as you might expect. Once the code warms up, it takes about a microsecond. But given that we're counting microseconds, that's still a lot depending on your use case, it might not be so much.
It's all a balancing act for sure. Deciding
Yes.
what's important, how much. Yeah. I think about this when I go shopping. This is expensive, but I'm going to buy it anyway.
Yes. Well, if it's going to help you solve a bug, then your time is probably worth more than the computer's.
So true. All right. Let's see. The next question we had, I believe this was in the context of the distributed unique timestamp section. It's from George Smith. He asked, he missed how the 2-digit server ID was created. Now, George, I'm not sure if that's the correct context. If you're still online, tell me if I'm wrong, but I think that's what you're referring to.
Yes, so the host ID has to be assigned either programmatically or through configuration. In the code that we have, we do it via a system property, and that system property can be set via a file. So when our library starts up, it looks for a file called system properties. And if it exists in the working directory, it loads it. And that can have a host ID in it, or it can be set on the command line, or it can be set programmatically. So it is left as an exercise for someone else to worry about how to set the host ID. However, we use the host ID for other purposes anyway, so it is already there. So it's not something we had to add in our case to suit just this class.
All right.
So there is also a requirement, the way this is implemented, that host IDs are between 0 and 99, which is another restriction.
Okay. Going through the rest of these, we had a nice comment by David about safe points. That it's a good trick. Thanks for sharing that. And then I believe this was asked when you were talking about the trivially copyable object. You may have had some code showing there. Vakagan is asking if these utilities are available in Chronicle Core or in one of the libs.
So trivially copyable is in bytes, Chronicle bytes. This code, one of the nice things about having open source is that you can Google your code. So if you take a decent portion of this code and Google it, it should come up with it, or something pretty close. It doesn't always get as good a match as you might expect, but it gets pretty close.
Cool.
Like you've got no idea whether it's going to give you the code, the Java doc, maybe an issue that was associated with it where it's quoted, but not the code itself. But it gets you pretty close.
Makes sense. Vakagan has another question. This was asked when you were talking about zero garbage coding. And then he has a specific question about, it's not just Chronicle wire, right? You have to reuse the objects you create.
Yeah, so this is something Chronicle Wire does. I'm not going to really cover it in this talk, but the way we encourage people to implement their microservices is via an interface. In this case, I might need to drop through to actual code. You can't see it because it's on the wrong screen. Let me find an example. Sorry. Is that big enough?
Yes.
So here's a trivial interface that I've used for this particular microservice. So it's a, go through the specific implementation. It has one event that it can handle, and it takes one DTO that it expects to have. Obviously, you can add more methods, and the more methods you add, the more message types you have. Message type matches the name of the method, and the way Wire works is that every time you make a method call, it actually writes out that method name and the DTO to whatever the stream is. It could be a queue, it could be some just in-memory bytes, it could be a network connection. And on the flip side, it replays it by reading the event name, which it then matches against a method to call, and it's got this DTO. So what it does is it creates one DTO for every method, even if the DTOs are the same. So that way, for every event type, you have one DTO created by the parser or reader, and that is reused and repopulated every time. So in this case, you get this object here. That's where all the actual data sits, and that way it is overwritten. So we've got support even for trying to keep lists of DTO, lists of rows of data reused as well, which is a little bit tricky, but it all works. So that way, so one of the caveats then is that the object that your microservice is called with is the same object every time. So you get called a million times, you get the same object again and again. So if you want to retain any data, you have to copy it. So you need to know that that's the case, that that's the life cycle. But it does give a very natural life cycle. So in this case, it makes this microservice is very easy in the sense that the message going out is the same DTO as the message coming in. So this event comes in, I add a timestamp, and then I call this method to say, right, this is the response. This is what I'm going to write out. And once this is returned, I don't need this event object anymore, and it can be reused. So I've kind of got an event pool, but it's one that's so lightweight, there's no real overhead associated with it. It's trivial to just overwrite it again and again and again, once for each method. This microservice itself is single-threaded, so there's no kind of thread safety, concurrency issues, sharing issues to worry about. And so, yeah, you're right. You do have to be aware that this is an object that's going to just get reused the very next time the method is called. So you have to copy it. So we've got some support for copying objects for that reason. But once you get your head around that, it works extremely efficiently.
Thank you, Peter. I love that you have all these examples at the ready for these questions. This is awesome. I'm learning a lot here. Another question, this is a good one from Alan Longhurst. Doesn't Java automatically intern strings now? 1.5 or something?
Actually, I'm pretty sure string interning was from the very first version of Java. However, it's only for objects that are string objects that are from code. So if you've got any string literals, so if I can find an example of a string literal, I may struggle. Okay, so here's a string literal, right? That string will have been interned. And if that string appears in any other class, it doesn't even have to be in the same class. It doesn't need to be compiled at the same time. It could be compiled with a different version of Java. But when this is used by the JVM, it is interned. And so you get back the same string object every time, wherever it's used anywhere in your code. However, if you create a string on the fly, it's not interned for you. So so you don't necessarily get string deduplication done for you. It is possible to do that, so the JVM might be able to do that, but that's not its default behavior, certainly for young objects that have just been created. My memory is a bit hazy that some JVMs might have this for older objects, but I'm pretty sure even in their case for young objects, they didn't do that because of the overhead of checking to see whether it's a duplicate or not. String interning does have limitations. So the data structure for it is doesn't scale very well. If you go mad, and I've done this, you create an enormous amount of strings that you programmatically intern, then the string interning gets slower and slower because it's not a data structure that's really intended to create millions of strings, for example. It's not intended for that purpose, because they never expected you to have millions of strings in your code, millions of constant strings in your code. So it's not good for that particular use case. Another problem is that another reason we don't use it is that to intern a string, you first have to create a string. So you create a string, you call intern on it, then it can return the string that's already in your in the internal string pool. But the problem is you've already created all the garbage. The only thing you're doing is you're deduplicating it so that after a GC, you have less copies in memory. So that's the only benefit the interner gives you. But it's kind of a bit too late in our case, because we don't want to be running GCs, and we don't want to be creating the object, the class string in the first place. So that's why in our case, we find it. I don't remember where it is in the presentation now. But in any case, what we do in the interface is we take a jar sequence that avoids having to create the object first. So a trivial example is if you populate a reused string builder. So you have a string builder you keep reusing every time you read a string, then you can call this method on that string builder, and then it can avoid creating any string at all. So there's no garbage being created. In our case, we have a class that's very similar to byte buffer that also implements char sequence so that it can come straight out of off-heap memory. So it's not even copied on heap to do this in the first place. Hopefully that answers the question. I can't hear you at the moment.
Oh, I apologize.
No,
This is a long question. Get everyone plenty of time to read it. Roshini made a comment that this is a very nice session. And if you have any source code links to post for later reference, and he's especially interested in the zero garbage coding technique that you shared.
Yes. So so all of the code I've shown today is in the OpenHFT GitHub repository, one of them. So you can Google OpenHFT and any of the code examples, and it should find you the original source code for that. Or you can just go through it yourself. And all of the code is using, well, not all of it, most of it is using zero garbage techniques. There are plenty of examples where we don't, because it wasn't worth optimizing. But for all the code that we expect to be called a lot, we've tried to make it zero GC. So yeah, so I can bring that up quite easily. There we go. So the libraries I mentioned today, cool. That's one that has a lot of these sorts of low-level stuff. And then there's, so this is all OpenHFT, GitHub. We've got all the unit tests in here as well. So some libraries don't publish their unit tests, like the code is public, but the tests are not. I'm not sure what the logic of that is. But there you go. And then there's wire and bytes. And these are all to do with low-level serialization. And then there's Q, which uses all of these. So this might be a place to start. So Q actually writes data to shared memory and then copies it from shared memory, and all that shared memory can be on a physical file. So it's all being streamed via files. So you can pass data from one thread to another, one process to another on the same machine without creating any garbage at all, or very little latency because it's all in shared memory. So give some examples of the sort of latencies that you can get.
Lots of resources here to browse. This is great.
Yes. There's a good thing about open source. It's all there.
Okay, another question from Vakagan, not related to this talk, but have you tried to build the Kafka equivalent, but with chronicle queues and replication? And if yes, what kind of performance improvement can one expect?
Okay, so I have done it with Kafka, and that's why I've got, and in fact I did. So it doesn't include replication because I haven't got that far, which is, I realize is the next thing I really should be doing. Sorry, a sec. So if you have a look at my blog, Vanilla Java. Sorry. So actually, you may find this interesting just because it did challenge me as to how best to illustrate the difference, because I've always given a somewhat flippant version answer that the latencies are just not comparable. But then, well, then how do you compare them if they're not comparable, right? So in this case, this is a benchmark for taking an event. You saw the event data structure, serializing it, writing it to a queue, reading it from the queue, deserializing it, putting it through the microservice. Again, you saw the microservice, it's trivial, it just adds another timestamp, and then passing it all the way back again to, and then what is the end-to-end latency of just passing a fairly simple event through a microservice and getting a response back. So this doesn't include replication, so it's the simplest case where you've only got one machine, right? Which is actually a very common use case for us. We're efficient and fast enough that generally you can buy a machine or get one from AWS or whoever your cloud provider is that actually holds the entire application, or the core of it anyway, can all sit on one machine. But so that's what I've started with. So for Chronicle Q to do all of that, the 99th percentile was about 3.7 microseconds, which is about the time it takes a signal to travel a small distance across London. It's about a 10-minute walk. However, using Kafka, the same thing, again, on one machine, simplest case, this is the fastest you could expect it to be, is the same as sending a signal all the way from London to Amsterdam. So it's quite a lot further, but it's about 750 times more. So I looked at publishing. So Kafka, of course, is originally used for log aggregation, and that's actually something it does really well. The difference in the typical latencies is something, but it's not dramatic. The outliers are quite bad for Kafka, but the typical latencies, 50 and 90th percentile, are pretty good. So it probably covers most people's use cases. However, when you look at the end-to-end latencies for a microservice, so this is not the time to publish, but the time to actually deliver a message, it really stacks up. So this is Chronicle's open source and our closed source. So the closed source has some features for keeping the jitter down, the higher percentiles down, and Kafka doesn't fit on the scale. So if you multiply it by 10, so this is scale up to 100, this is up to 1,000. Again, still Kafka's off the scale. So multiply it by another 10, so now we're at 10,000 microseconds. The problem is you can now see how Kafka performs, but you can't actually see how chronicable forms. It doesn't really show up. It's sort of sitting on the bottom there. In fact, you can't tell the difference between open source and closed source there. It's just flat. And then if you include when a situation where it looks like Kafka is probably a bit overloaded, the only way to get it all onto one chart is to use a log scale, but not everyone's familiar with reading log scales, so you wouldn't necessarily see by eye the dramatic difference between them, but really it's the only way to illustrate it. So that was my biggest challenge writing this, is figuring out, well, how do I illustrate what the difference actually is?
All right, this is an excellent plug for your vanilla Java blog. If the audience here hasn't checked that out, do so. There's a lot of good information here. You can go and read further and explore further on this.
Yeah, I've had 4 million views so far.
Awesome. Yeah, pretty valuable stuff. So Kirk Pepperdine has a question, and I believe this has to do with the cleanup of the threads you were talking about during your session. Hi, Peter. Have you looked at using Cleaner?
Yes. So Cleaner has a few problems. I think the biggest problem for us is that we have a lot of our clients require Java 8, which is a bit of a pain because Java 8 Cleaner and Java 9 Cleaner are different. They're different classes. They try to clean up the Cleaner, but it's not backwardly compatible to Java 8. That's really been a bit of the problem. Another problem is that Cleaner isn't called deterministically when a thread dies, which is one of the things that we want to be able to do. So the example use case is some clients end up putting a file handle or something that's holding onto a file handle into a thread local, and then the thread dies, and then they want to delete the file. And on Windows, they can't delete it until it's actually closed. And so they're waiting around. They either have to trigger a GC so they can delete the file, or in any case, it's quite horrible. So certainly, if there was a cleaner that activated as soon as the thread that used it died, then that would be. It's not too hard to implement, as you can see. It's just a matter of trolling through all the thread locals and just killing them, cleaning them all up. But yeah, that's unfortunately this is very hacky, but it works.
All right, we have a pretty specific question from Ahmed. Can we use the field byte value of the string class in order to serialize, deserialize a string?
Can't quite picture that question. Here we go. You could, and in fact, we do in some cases, yes. I wouldn't necessarily advise it unless you've got a really good reason to do so. Yes, it can be done, but you need to take into account that won't work on Java 8, and you can't guarantee that the value will actually be a byte array. However, if you want a really efficient way of converting to UTF-8, and your strings happen to be of that type, then it can be extremely efficient. So you could have a fallback. You could say, if it's a byte array, I'm going to be cheeky. If it's not, then I'm going to fall back to generic code, which I need to write anyway, just to be able to handle the default case. One of the caveats is that you might not be writing UTF-8. You might be writing a slightly different character encoding, in which case you end up with a convoluted example anyway, because you're having to decode and re-encode as you go. It's quite painful in that case. So as long as you use the assumption that you're also going to be deserializing it in the same format as it was written in the first place, then which is the sort of thing we do with trivial or copyable, then it's okay.
Excellent. All right. We
So
just
one of
have,
the nice things about accessing Byteway directly is that if you use a low-level copy, like even a memory copy, then you can be copying 8 bytes at a time. So it's faster than copying 1 byte at a time out of the byte array.
excellent. All right. One last question from Smith. There was a restriction that was lifted in Java 17 about static members inside inner classes, and why was that lifted? And how come that was, not possible in any version before Java 16?
Good question. I really don't know the answer to that, to be honest.
If we have any other Java champions out there, feel free to answer this
I'm sure
question.
someone knows.
All right. One more compliment for you from Bakugan. Thanks for all your contributions to open source. Chronicle libraries are very, very underrated. If you haven't
Thank you.
check those out, please do.
Yes, we do get a lot of downloads every month. We're getting, well into the thousands for all of our libraries. So.
Excellent. Thank you so much for your time, Peter. This was wonderful. I know I learned a lot just sitting here moderating your session. So
Thank you.
This was great and much, much appreciated. Thank you, everyone, for joining. And go check out some of the other sessions happening right now with all of the other Java champions.
Okay. Thank you very much, everyone. And especially you, Melissa.